Salatu wassalamu ala nabiyyina Muhammad wa ala alihi wa sahbihi ajma'in. So far we have already introduced several concepts with ROS, in ROS computation graph, including ROS topics, ROS services, how to publish a message over a certain topic, how to subscribe to a message, or also how to create a client-server application using ROS services. So now you have already a good knowledge about ROS computation graph and the ROS ecosystem as a whole, and what is happening actually between the different nodes by exchanging messages, either using topics or services. So now we are going to go into one of the most important and exciting part of this course, that is ROS motion, and it's about how to make a robot move. And of course, we are going to use the same concept that we have learned so far to make the robot move. In the previous assignment, I have already provided you to develop a few methods to make the robot move for a certain distance and also to rotate in place. We're going also to go over these two methods, and we will elaborate more on them to go for more advanced motion of the robot. So this is what we are going to do. We are going to consider a simple cleaning application. There are some kind of cleaning robots like the Roomba robots. We can put it in an open space, and then it needs to make the coverage of the whole space in order to clean it, to clean the ground. So we will simulate this using TurtleSim, and we will try to develop an application that will make the TurtleSim going through the different locations and in the open space area here in the map. Okay, so this is the application, and of course, as you can see here, we have different types of motion. We have a motion that takes the robot from one location to another. This is what we call go-to-goal. We are going to explain this in more details. We have also a linear motion, we have rotation motion. So let's see what are the different types of motion that we are going to cover in this lecture. Another possible way to make the cleaning robot move is to use a spiral trajectory, and the robot is going to move in this way. So I will introduce you the equation of the spiral trajectory and how you can develop this in ROS to make the robot moving into using this trajectory. So now let's go through the different types of motions that we will have to implement. Of course, now the ultimate application is to make the cleaning application, but this cleaning application is composed of different elementary motions. So we're going to introduce these elementary motions first, and then we will develop the whole application that will integrate all these different elementary motions. So first of all, remember that the motion of the robot is ensured by the twist message, which is composed by a linear velocity and angular velocity, and both the linear velocity and angular velocity, they have x, y, and z components because we have 3D space, the motion in 3D motion in 3D space. Now the first elementary motion is to move in a straight line, like the following. Okay, so in order to do that, it's simple. What we need to do, we need just to specify a constant speed for the x component, x coordinate of the linear speed, and the robot is going to move straight. And all the other values have to be set to 0. Of course, by default, when you create a twist message, all the values are equal to 0, so we just need to set the x component of the linear speed, and the robot is going to move into a straight line. The second elementary motion is to rotate in place. So the robot is going to rotate like this in place. And here we are going to put 0 all the different values for linear and angular velocity, except the angular velocity at the z component has to be equal to a certain constant speed. Okay, and the robot is going to rotate in place. So the rotation around the z-axis, this is what we call the yaw, and we just need to specify a constant speed for the robot to rotate in place for the angular velocity, of course. Another type of motion that we are going also to develop in this lecture is the go-to-goal behavior. So in this case, we have a start location, that is the initial location of the robot, and a goal location. We specify just a goal location. And then we will develop a method that will make the robot move smoothly from the start location and the goal location. So to do so, the twist message here, we will have to put a velocity for the linear velocity in the x component, which will be just a function of the distance. Okay, and for the angular velocity, it will be just a function of the angle between the orientation of the robot at this at this location and also at the desired location. So here, just to give you some intuition, because later I'm going to talk more about the details. So if the distance is greater than 0, in this case we have to provide a linear speed that is greater than 0, so it will make the robot move. But if the distance becomes 0, in this case we have to put the value of x to 0, so it's gonna stop. So this means that the linear velocity in the x component will be just proportional to the distance, and the distance will be kind of an error measure between the current location and the desired location, that is the objective that we want to reach. And the same thing will be also applied to the angular velocity. So we will consider the current orientation of the robot and the desired orientation, then make the difference between both, and then the angular velocity will be a function about this difference until the robot becomes really looking straight to the goal location. And this concept falls under the concept of PID controller, proportional, integral, and derivative. Here in our case, we are going just to develop a proportional controller, but I'm going to provide you some more intuition about the whole PID controller and how it works during the course. So the last trajectory is going to be the spiral trajectory. And here, in the twist message, we are going to put the linear velocity in the x component as a function of time, while we are going to provide a constant speed for the angular velocity at the z component, at the z coordinate. And doing that, we will have a trajectory similar to what you see in this animation. So these are the different elementary trajectories that we are going to develop in this lecture, and I will show you how to implement all these different behaviors to finally develop the cleaning application. In the previous lecture, I have introduced to you the cleaning application, and also I presented the different trajectories and motion behaviors that we will have to implement in order to accomplish this application. And in this lecture, I'm going to show you how you can implement this in Python and C++. Okay, so let's get started. Usually before going to development and programming, you have first to understand the topic and the messages to be used. Okay, so now when we run the turtle sim, we need to understand what are the topics available and what are the messages available that we have to implement them. So the first thing we can do is to use ROS topic list, and here we can observe, as we already seen before, that the topic to make the robot move is the turtle1 CMD-val. And if we look at the information of this topic using ROS topic info, it will show for us that it is using the geometry underscore MSGS/twist message. So this message, we are going to use it in Python in order to develop the motion application. So it's really important that to know and to understand what are the topics that you are going to deal with in your code, and using ROS topic list, ROS topic info, and the different commands to get this information. And we can also go more inside the twist message, as we already did before, using ROS MSGS show geometry message/twist. And here we can see that we have a linear velocity component and angular velocity component, as you already know. And this is just a simple reminder about the motion in space, why we use X, Y, Z, because any robot can move in, any robot in three-dimensional space can move either linearly toward the X-axis or the Z-axis or the Y-axis. Okay, but of course, when we deal with ground robot, we have only a motion in two-dimensional space. And basically, the linear velocity is going only to be in the X direction. Y usually is equal to 0 because we don't have holonomic robots, and Z is going to equal to 0 because the ground robot cannot fly. So in the same way for the orientation, we have three possible rotations. The rotation around the Y-axis is the pitch, the rotation around the X-axis is the roll, and the rotation around the Z-axis is called the yaw. This is just the rotation in three-dimensional space. Of course, for a two-dimensional space motion, we have rotation only around the Z-axis, so we only talk about the yaw. This is the orientation of the robot, of the ground robot. Another topic that is also important that we will use in our application is the pose topic. And the pose topic is used to provide the information about where the robot is located in a two-dimensional space. So using ROS topic list, we can understand that the pose of the robot is captured by the topic turtle1 /pose. And looking at the information of this topic, we can understand that it has a type turtle theme /pose. So let's see what is the content of this message. Using ROS MSG show turtle theme /pose, we can find that it contains x, y, that is the coordinate in two-dimensional space. Theta is the orientation of the robot in two-dimensional space, that is basically the yaw, because this will be the rotation around the z-axis. And here we have the information about the linear velocity and angular velocity, and these two values will be just the copy of the linear.x component in the twist message for the linear velocity, and the angular velocity will be just angular.z component in the twist message. We'll be just having a copy here, so you can read them either from the pose message or you can read them from the twist message. Okay, so when the robot is moving, this linear velocity will change to the current velocity of the robot, both and also the angular velocity as well. So this is just a small reminder about how to represent the coordinate of the robot in two-dimensional space. Imagine that you have a robot here. So this robot, for example, it has x equal to 8, is located in x equal to 8, and y equal to 5, and has an orientation, theta, of 45 degrees. This is how we measure the orientation. We measure it with respect to the x-axis, because the rotation is actually done around the z-axis. Okay, so here we have 45 degrees with respect to the x-axis. And of course we can map, so this x represent to the x in the pose message, y also represent to the y of the pose message, theta represent the orientation of the robot, linear velocity and angular velocity. So the linear velocity represents the x component of the linear velocity in the twist message, and the angular velocity represents the z component of the angular velocity in the twist message. So now let's start about the implementation. I'm going to show you both the Python implementation and the C++ implementation. The first thing you need to do is to import the libraries of the message. So in the previous slides, we have already seen that we are going to use the twist message and the post message. So it's really important to import them first in your files. So in Python code, you will need to import ROS.py, which is the client library of ROS in Python language. And you need also to import the twist message and the post message using the following instruction from the package geometry underscore msgs.msg. This is the file where the twist message is located, as we have already demonstrated before, and then import the twist message. And the same thing will be for the post message, which is located in the package turtle theme in the folder msg. And for the C++, it's similar. We need to include ros.h, which is the C++ library of ROS, and we need to include also the twist.h message located in the package geometry underscore msgs, and we need to include also post.h header file, which is located into the turtle theme message. This is how we can import the library of messages in both Python and C++. Okay, so now we are ready to start implementing the different trajectory behaviors, but before doing this, let me just give you what is our roadmap. So we have to develop a cleaning application that is composed of different types of motions. So we are going to follow the approach of divide and conquer. This means that we are going to divide this big problem into several sub-problems, and then we will integrate all of them together to develop the whole application. So these are the different steps that we are going to follow. First, we are going to develop a function to move in a straight line for a certain distance in forward and backward directions. This is the first method that we will develop, is just to move in a straight line. The second method will be to develop a function to rotate in place for a certain angle. Okay, and here we can either rotate in clockwise direction or counterclockwise direction. The third step, we will develop a function to go for a certain goal location. And the fourth step, we will develop a function to move in a spiral trajectory shape. The last step will be to integrate all the previous steps together in order to develop the cleaning application, which will integrate go-to-goal behavior, move in a straight line, rotate in place, and so on. So this is how we can divide like a complex problem into several sub-problems, and then we will try to integrate the different solutions together to develop the global solution. So now let's get started with the first function, that is moving in a straight line.